You have a fully trained classification model and it seems to work, but how do you know whether it's a good one? You need a few metrics to evaluate your model, and the metrics that you use for classification models are accuracy, precision, and recall. Let's talk about accuracy first, as that's the simplest and the most intuitive to understand. You'll calculate the accuracy of your model by comparing the predicted labels, which are the output of your model, versus the actual labels or the actual categories that you have in your data. Higher the number of matches of actual values versus predicted values, higher the accuracy. As a student of machine learning, when you first get started with classification models, accuracy is the first metric that you learn about. High accuracy is good, but there is an important asterisk here which you need to understand. An algorithm might have a high accuracy but still be a poor machine learning model, and its predictions might be useless. Based on what your ML model is trying to classify, accuracy may not be a good metric. Consider this all is well binary classifier where you feed in medical reports to this classification model. And this classification model always believes that all is well. It always classifies the medical reports as normal, the person has no cancer. Now, for a rare cancer, which occurs only in a very few individuals, the accuracy of this model might be very high, might be 99.999%. But really, is this a useful model? No. And this brings us to when accuracy is not a great metric. There might be certain labels in your dataset that are common or rarer than others. Such a dataset is said to be skewed. For example, in our medical records dataset, only maybe 1 in every 100 individuals has this rare type of cancer. When you're working with skewed data, accuracy tends to be a poor evaluation metric. That's when you need to consider other metrics, and for that we'll set up a confusion matrix. A confusion matrix is simply a grid tabulating the predicted labels from your model versus the actual labels. So you have predicted labels along the columns, and along the rows you have the actual labels from your data. Now, because there are just two possible outputs for this particular classification model, this is a binary classifier. This is why this confusion matrix has 2 rows and 2 columns. You can have as many rows and columns as there are categories in your underlying data. This cell here on the top left gives you the number of instances where our model correctly predicted the existence of cancer. Actual label equal to predicted label, and these are the true positives in our prediction. The cell here at the bottom left represents the number of instances where our model predicted cancer, but cancer did not actually exist. Actual label is not equal to the predicted label. These are the false positives, or FP. The cell here at the bottom right are the number of instances where our model predicted no cancer and there was actually no cancer. Actual label equal to predicted label. These are the true negatives. And here on the top right are the number of instances where our model said no cancer was present, but the patient was actually diagnosed with cancer. These are the false negatives. This is what each cell in a confusion matrix represents: predicted labels versus actual labels, and you can use this to calculate accuracy, precision, as well as recall. Let's start with accuracy. Take a note of all of the cells where the actual label is equal to the predicted labels. This will give you the accuracy of your model, TP plus TN upon the total number of instances on which prediction was performed. Just based on the data that we have here, the accuracy of this model is 99.12%. An accuracy of 99.12%, which you have to admit is extremely high, means that the classifier gets its predictions right 99.12% of the time. But let's take a look at the confusion matrix. Observe the false positives here. Here are people getting treated for cancer on chemotherapy or radiation when it's absolutely not required. They don't actually have cancer. And at the other end, here are all of these patients who need treatment for cancer, but cancer wasn't detected using our model, so no treatment was prescribed. Given this, it's pretty clear that accuracy is not a good metric to evaluate whether this model performs well. We need other metrics, and that's where precision comes in. Precision can be thought of as the accuracy of your model when it flags cancer or when it makes positive identifications in your dataset. The precision of your model improves when there are fewer false positives. The cancer is detected when it doesn't exist. If you calculate the precision of this model, you'll see that it comes to 66.67%. Our model is not looking that good now, is it? This precision value tells us that 1 out of every 3 cancer diagnoses made by our model is incorrect. Another metric that you can use to evaluate this model is recall. Recall considers the 2 cells on the top. Recall is the accuracy of your model when cancer is actually present. You can imagine that this is a measure of how well our model managed to identify patients who actually had cancer. To improve your recall score, you need higher true positives and fewer false negatives. The recall of this model is 71.42%. And once again, this model isn't really looking that good using this metric. A recall value of 70% essentially means that 2 out of every 7 cancer cases was missed by our model. Our model didn't detect it.